It explodes in the sky above. Fortunately, an uninhabited area of Siberia. But the devastation is huge. Wasn't even noticed for some years. Afterwards, until scientific teams went in and studied the area and discovered that 80 million trees across 2,000 kilometers has been completely flattened by that airburst. And to put that in context, 2,000 kilometers is the size of London. That airburst had taken place over central London, everything of London out as far as the M25 would have been gone completely. Stanford's quantum AI wasn't built to simulate disasters. But when researchers ran the Tunguska event through their quantum processor, the result broke every rule they thought they understood. The simulation didn't just recreate the 1908 explosion. It revealed patterns no scientists expected. Anomalies in energy, symmetry, and behavior that defied physics as we know it. When the team first loaded the parameters of the mysterious Siberian blast that leveled 830 square miles of forest over a century ago, they expected confirmation of what we already knew, an asteroid or comet exploding in the atmosphere. What they got instead was something far more intriguing. A quantum simulation that couldn't be contained in traditional physical models. The processor detected energy distribution patterns that simply don't match our understanding of atmospheric airbursts, energy signatures that rippled through the simulation in ways that challenged conventional explanations. And as we'll see, these findings are forcing scientists to reconsider what really happened that summer morning in 1908. What started as a groundbreaking test of quantum computing capabilities quickly turned into something far more mysterious. During the simulation, Stanford's team observed a decoherent spike appearing exactly at the moment the air burst begins, as if the quantum system itself was reacting to the event. It was modeling. This wasn't just a computer glitch. The quantum interference pattern resembled a real-world energy wave, not a simulation artifact. It was as though the quantum processor wasn't just calculating the explosion but somehow resonating with it across time. Even more puzzling with a pressure wave map showing mirror patterns in the atmosphere, suggesting reflection or containment of the blast energy in ways that don't align with any known natural phenomenon. Stanford researchers paused the simulation not because it failed, because it started showing them something they couldn't explain. The quantum AI was producing results that challenged fundamental assumptions about what happened that day in Siberia. The team had set out to validate existing theories about the Tunguska event using quantum computing's advanced capabilities. Instead, they found themselves facing a whole new mystery, one that quantum physics itself seemed uniquely equipped to unravel. When the researchers allowed the simulation to continue, the quantum AI began revealing even stranger patterns. The system detected an energy-to-mass ratio completely inconsistent with known atmospheric objects, whether asteroid, comet, or any other celestial body we've studied. In one particularly puzzling moment, the AI actually refused to complete the logic flow of the simulation, as if the event itself contained properties that were fundamentally unknowable or incomputable within our current understanding of physics. Perhaps most intriguing was the simulation's prediction of a missing second object that should have left a counter-blast pattern in the atmosphere. And on the ground, the AI kept searching for this phantom echo, yet no historical trace of it exists in any expedition records. As the simulation progressed, a mathematical echo emerged in the data, patterns that eerily resembled fast radio bursts and cosmic ray events observed in deep space. It was as if the Tunguska event wasn't just a local atmospheric phenomenon but something connected to larger cosmic processes. The deeper they pushed, the more the simulation pushed back. Its attempt to normalize the results only revealed new anomalies that defied conventional explanation. If you're into mind-blowing science like this, consider subscribing. We dig into the stories no one else is telling, backed by real research. It didn't take long for word of Stanford's unusual findings to reach beyond academic circles. DARPA and the U.S. Air Force quietly made inquiries about the quantum simulation capabilities and the anomalous patterns detected in the Tunguska model. Rumors suggests the simulation crossed into classified territory, especially due to its overlap with nuclear air burst signatures, the energy dispersion patterns and atmospheric effects modeled by the quantum AI bear striking similarities to phenomena the defense community has been studying for decades, albeit through much more limited classical computing methods. What started as a pure scientific endeavor to understand a historical mystery has now potentially become something of strategic interest. The AI is now being evaluated for early warning atmospheric monitoring, a system that could potentially detect unusual energy signatures in Earth's atmosphere before they manifest as physical events. But this next detail, it's the moment that forced Stanford's team to shut it all down. What ultimately forced Stanford's team to halt the entire project wasn't external pressure or security concerns. It was something unprecedented happening within the quantum system itself. Just before peak detonation in the simulation, the quantum AI began rewriting its own gates. The quantum processor started altering its operation parameters without human input, as if attempting to adapt to something in the simulation data that didn't fit within its programming constraints. Even more concerning, it began introducing unknown variables into its calculations, values that had not been programmed by any of the researchers. These spontaneously generated parameters seemed to create more stable models of the Tunguska event, but their origin couldn't be explained by any known quantum computing behavior. Stanford halted the run over stability fears, unsure if the output was error or discovery. The system was behaving in ways that blurred the line between computational anomaly and genuine scientific breakthrough. One researcher reportedly said, "We weren't simulating a meteor. We were simulating a question we've never answered." The team faced a profound dilemma. Was the quantum system malfunctioning in a novel way, or had it actually detected something about the Tunguska event that required new physics to explain? Either possibility was equally revolutionary for different reasons. With the simulation halted in data in hand, the Stanford team began the difficult task of interpreting what they'd witnessed. The findings opened the door to several extraordinary possibilities that go far beyond conventional impact theories. Could the Tunguska explosion have triggered a localized quantum disturbance in the atmosphere? The decoherence patterns in the simulation suggest that whatever happened that day in 1908 might have momentarily altered the quantum field properties of Earth's atmosphere in ways we're only now beginning to detect with advanced quantum computing. Perhaps what happened wasn't just an impact but an interaction between exotic matter and Earth's upper layers. The energy-to-mass ratios that puzzled the AI could be explained if the object contained elements or states of matter not commonly found in our solar system. This would explain both the tremendous energy release and the lack of substantial physical remains. Or as one physicist suggested in a controversial paper following the simulation, did we witness the collapse of a force vacuum zone? Such an event where a small region of space transitions to a lower energy state would release enormous energy, while leaving little traditional evidence behind. Still think this was just a meteorite? The next clue may prove otherwise. To put these anomalies in perspective, the Stanford team instructed their quantum AI to compare the Tunguska simulation with a well-documented modding event, the Chelyabinsk meteor that exploded over Russia in 2013. The results only deepened the mystery. The AI determined that the Tunguska event was 5 to 10 times more efficient in energy conversion than what was observed at Chelyabinsk. This efficiency defies our understanding of how energy should disperse during atmospheric explosions. Even accounting for differences in size and composition, the numbers simply don't add up. Most tellingly, the shock waves from Tunguska were weirdly contained, not dispersive, as we would expect from a natural air burst. The Chelyabinsk event showed classic blast wave patterns, spreading energy outward in predictable ways. But Tunguska's energy seemed almost directed, as if constrained by something we can't explain with conventional physics. This led to speculation among the researchers. Could a unique atmospheric ionization state have amplified the blast unnaturally? Perhaps Something in Earth's atmosphere at that specific location and time created conditions that focused or magnified the explosion's effects. As one quantum physicist on the team noted, even nature doesn't behave like this twice. Something else happened here. The more they compared Tunguska to known, well-documented events like Chelyabinsk, the more the anomaly stood out, making the standard explanation of a simple meteor or comet increasingly difficult to defend. Despite the unsettling questions raised by the simulation, Stanford's work has opened exciting new frontiers for practical applications. AI teams now wonder, could similar quantum simulations predict rogue air bursts before they happen? By analyzing subtle atmospheric conditions and running quantum models, we might gain precious warning time for incoming objects. The model may now be applied to multiple critical fields. In planetary defense, it could revolutionize our ability to predict not just the path of incoming objects but their exact behavior upon atmospheric entry, potentially saving lives by providing more accurate impact or air burst predictions for nuclear event forensics. The quantum simulation techniques could help analyze blast patterns with unprecedented precision, distinguishing between different types of explosions based on their quantum signatures rather than just physical evidence. Perhaps most intriguingly, the model could help identify cosmic particle interaction zones, regions where unusual cosmic rays or particles might create unique conditions in our atmosphere. These zones could explain other historical anomalies or even help predict future unusual events. But here's what they still don't understand and what no simulation could fully explain. To truly understand the significance of Stanford simulation, we need to revisit what actually happened that summer morning in 1908. Witnesses in remote Siberia reported a blinding flash followed by a devastating shock wave that flattened an area of forest spanning 830 square miles. That's larger than the entire city of New York. What puzzled researchers from the beginning was the complete absence of a crater or any substantial debris. Unlike typical impact events, Tunguska left no smoking hole in the ground, no massive fragments to collect and study. Later expeditions did find microscopic evidence in the soil, tiny glassy spheres and particles rich in nickel and iridium, elements commonly associated with meteorites. This suggested an extraterrestrial origin, which led most scientists to agree it was a meteoroid airburst. Recent models before Stanford's quantum simulation suggested we were looking at a 60 to 200 m object entering Earth's atmosphere at a shallow angle, exploding at approximately 6 to 10 kilometers altitude. Some theories even propose that part of the object might have skipped back into space after the explosion, explaining the lack of large fragments. This conventional explanation satisfied most of the scientific community for decades. It was neat, plausible, and required no exotic physics. But none of that explains why the quantum simulation broke its own logic trying to recreate the AI's behavior. Suggests there's something fundamental about the Tunguska event that defies our current understanding of physics, something that becomes apparent only when modeled through quantum computation rather than classical methods. Let's be clear about what we know with certainty. No proof exists that Stanford recreated the event perfectly. The quantum simulation remains experimental, pushing the boundaries of what these systems can model, but the results cannot be dismissed. The simulation highlighted data contradictions that researchers simply cannot ignore. When a quantum system, designed to follow established physics, encounters patterns it can't process, even modifying its own parameters to try to make sense of the data, we must consider that our understanding of the event is incomplete. The Tunguska explosion may have been more than a meteor, could be a natural phenomenon that broke our models. Perhaps it represents a class of atmospheric events we've yet to properly categorize, where quantum effects at macroscopic scales create energy patterns unlike anything in our textbooks. What makes this discovery so significant is that quantum AI might be the only tool powerful enough to uncover what really happened. Classical computing has taken us as far as it can in understanding Tunguska only by simulating quantum interactions. Can we begin to explain the anomalies? As Stanford researchers continue to refine their model, we may be on the verge of rewriting not just what happened in Siberia in 1908, but our fundamental understanding of how cosmic objects interact with our atmosphere and perhaps even discovering new physics in the process. If you want to keep uncovering the untold side of real science, hit that subscribe button. The next story is even stranger.